Mix two losing games and you start winning. Today's story begins now. There's an honest casino. There are only two games, A and B, and the sign says both are guaranteed losers in the long run. Yet one guest does nothing but switch between the two games, and the chips keep piling up. Two losing games mixed together became a winning game. He added minus and got a plus. No trickery. In 1996, the Spanish physicist Juan Parrondo actually designed it. We'll bring in 20,000 virtual gamblers and dig down to the very bottom of this true claim. First, the simplest game, Game A. Game A is a coin game. Win and you receive one chip, lose and you hand one over. But the coin is slightly biased, so the chance of winning isn't 50-50, it's 49.5%. Over 1,000 rounds, an average gap of 10 rounds makes 10 chips vanish. That 0.5 percentage points is the casino's cut. A coin has no memory, so the moment of recovery, I'm due for a win, never comes. The real star is the oddball that peeks into your wallet. Game B. Game B is also a coin game with just one difference. There are two coins. Which coin gets flipped is decided by the dealer, who looks at the player's chip balance. If your balance is a multiple of 3, you get the bad coin with a 9.5% chance of winning. Otherwise, the good coin at 74.5%. 1 in every 3 numbers is a multiple of 3, so let's assume the bad coin shows up once every 3 rounds. Under that assumption, the average win rate works out to about 52.8%. It's over 50. At this rate, Game B should be a moneymaker, growing your stack by about 57 chips over 1,000 rounds. But the sign said B is a losing game too. They can't both be true, so there's a hole in the calculation. Let's uncover that hole. The trap lies in the multiple of 3 squares. The balance doesn't jump around at random like a die. It moves just 1 square each round. At balance 6, the bad coin usually loses, dropping to 5. At 5, the good coin usually wins, climbing back to 6, it oscillates. So the time spent on trap squares isn't 33%, it's exactly 5 out of 13. Recalculate with this fraction and you get exactly 50%, a break-even game. With the stickiness included, Game B is a precision machine tuned to exactly break even. Add the cut on top and it becomes a losing game. We had 20,000 gamblers play only Game B, 1,000 rounds each. The numbers printed to the console tell the truth. On the left, the time spent in the trap. On the right, the balance curves of prophecy versus reality. They spent 38.4% of their time on the trap, and their balance sank to minus 9.4 chips. Now the highlight. The magic moment where mixing brought them back to life. A loses about 10 chips over 1,000 rounds, B about 9. Both are losing games. Parrondo's proposal: before each round flip a fair coin, heads play A, tails play B. For comparison, we also prepared simple alternation ABAB, and the repeating ABAB rhythm. This code runs the 5 teams. Each round it picks a game by the rule and flips a coin, nothing more. Let's get the results in the console. We overlaid the 5 teams' average profit and loss curves on a single screen. A only, B only, and simple alternation stay below break-even, but the 50-50 mix is plus 15, and ABAB is plus 65. You win even when mixing at random. The magic comes from the very act of switching back and forth, though simple alternation still loses. It matters not just that you mix, but how you mix. What on earth is going on? Game B's curse lay not in the coins, but in the rhythm of the balance circling the trap squares like a pendulum. Pour the nearly 50-50 Game A onto that pendulum, and it wildly stirs up the beat and scatters it. A friend who shakes you randomly pries your foot off the stickiness at just the right moment. Mix 50-50 and the trap dwell time drops from 38.4% to 34.5%. Do we have to mix in exactly half A? Let's compute every ratio using the Markov stationary distribution. This code sweeps the A fraction from 0 to 100% and pulls out the win rate in one go. The winning range is an A fraction of 8 to 84%, with the optimum around 41%. On the left, the stirrer's effect. On the right, the whole landscape of the paradox. Both ends are underwater, but the space between is a rounded hill. Mix in even a little and you surface, it's a robust phenomenon. But why would a physicist invent games like these? His 1996 Turin workshop talk was titled, How to Cheat a Bad Mathematician. What he was looking at was the Brownian ratchet. The dream of extracting free energy from jitter was proven impossible by Feynman and others. The twist: flicker an asymmetric sawtooth slope, and the jittering particles march in one direction. Game B is the sawtooth slope, A is the shaking. Parrondo translated this physics into coins. In 1999, Harmer and Abbott published their analysis in Nature, and the paradox became known to the world. The question you're dying to ask: could you actually use this to rob a casino? You can't. The magic has a price tag too, so what happens if we raise the cut? We raised the cut from 0 to 4.5 percentage points and plotted the profit and loss of 4 strategies. The 50-50 mix tops out at 1.31, and even the most robust ABAB can take only 3.64 percentage points. But the real reason lies elsewhere. Even in a fair casino with 0 cut, the 50-50 mix comes out positive. The source is one thing, Game B peaks at your balance. It's the link that ties the probability to your balance. Real roulette and slots don't look at your balance. With no teeth to mesh with, it's just the average of losing games. What about stocks? Mix 2 falling stocks and do you get a rising portfolio? In 2000, the New York Times ran the on-paper calculation, but the researchers themselves drew a line. Applying it to markets is premature. So where is it used? Molecular motors inside cells, ecology and evolution, reliability engineering, and even quantum Parrondo games. The common denominator is one thing. The parts must be linked. With no link, 2 bad things are just 2 bad things. At last, the finale. Let's pull today's story together one step further. Game B's surface calculation, 52.8%, promised a moneymaker. But carry the stickiness all the way through and it's exactly 50. Add the cut and it becomes a losing game. Yet mix the two and you win, because A's shaking frees B's stickiness. The real lesson isn't a foolproof gambling system. It's that even when the parts are all bad, the whole can be good. The intuition that combining bad things makes them worse is safe only when the parts don't influence each other. The mathematician who stops at the rough estimate gets cheated. The one who goes all the way also sees how to win. If today's video helped you, please subscribe and like. See you in the next one.